OTN and DWDM. In the evolution of telecom networks, if ATM was the intelligent brain of the 90s, then DWDM and OTN are the superhighways and logistics systems of the modern era. While ATM dealt with small 53-byte cells, modern optical networks deal with massive streams of data, 100G, 400G, and beyond. DWDM, dense wavelength division multiplexing. DWDM is a physical layer technology that increases the capacity of a single fiber by sending multiple signals simultaneously at different colors, wavelengths, of light. How it works: think of a fiber optic cable as a dark tunnel. Instead of sending just one white light signal, DWDM uses a prism-like device, multiplexer, to shine up to 80 or 96 different colors of light through that same tunnel. Each color is an independent lane of traffic. Capacity: each color can carry 100 Gbps or more. A single fiber strand can therefore carry nearly 10 terabits per second. The optical layer, DWDM, is purely optical. It doesn't look at the data inside, it just moves photons. In DWDM, dense wavelength division multiplexing, the spacing refers to how close the colors, wavelengths, of light are to each other. Because they are so close, they require two specific technologies to work: a precise frequency grid and the EDFA amplifier. Wavelength spacing, the ITU grid. In a standard home fiber connection, wavelengths are wide apart. In DWDM, they are crammed together using a standard set by the ITU, International Telecommunications Union, called the G.694.1 grid. Fixed grid spacing: DWDM uses frequency intervals rather than simple wavelength numbers to ensure precision. 3. The most common spacings are 100 GHz spacing, 0.8 nm. This allows for about 40 to 48 channels in the C-band. It is easier to manufacture and more robust against signal interference. 50 GHz spacing, 0.4 nm. This doubles the capacity to 80 to 96 channels. It requires high-precision lasers that won't drift into the next channel's lane. 12.5 GHz/25 GHz, used in ultra-dense WDM for even higher capacity. The flexible grid: modern 400G and 800G signals are too fat for 50 GHz lanes. Modern networks use a flex grid, where the spectrum is sliced into tiny 6.25 GHz chunks. A high-speed signal can rent as many chunks as it needs, example 75 GHz or 112.5 GHz, maximizing every bit of the fiber. The EDFA, boosting multiple waves simultaneously. The erbium-doped fiber amplifier, EDFA, is the magic component of DWDM. Before it existed, we had to convert light back into electricity, amplify it, and turn it back into light for every single wavelength, which was incredibly expensive. How it works: the chemistry of light. An EDFA is a segment of fiber optic cable that has been doped with erbium ions. 1. The pump, a high-power pump laser, usually at 980 nanometers or 1480 nanometers, is shown into the erbium-doped fiber. This excites the erbium ions to a higher energy state. 2. The weight: these ions stay in a metastable state, essentially cocked and ready to release energy. 3. The trigger: stimulated emission. As the DWDM signals, the multiple wavelengths, pass through this fiber, the photons of the signal tickle the excited erbium ions. 4. The boost: the ions drop back to their ground state and release a new photon that is an exact clone, same wavelength, same phase, same direction, of the signal photon. Why is it special for DWDM? Unlike a laser, which only works at one specific color, an EDFA has a wide gain bandwidth. It provides a cloud of available energy across the entire C-band, 1530 nanometers to 1565 nanometers. Because of this, an EDFA doesn't care if there is one wavelength or 96 wavelengths passing through it. It boosts all of them at the exact same time using the same energy pool. This allows a single $5,000 amplifier to do the work that would otherwise require 96 separate electronic repeaters. Summary comparison feature: DWDM spacing, EDFA role: keeping signals strong over long. Primary goal: maximizing the lanes in a fiber. Distances: standard ITU G.694.1, 100 GHz/50 GHz. Operates in C-band and L-band. Key benefit: high capacity, terabits per fiber. Multi-channel amplification, low cost/bit. To build a functional DWDM system, several specialized components must work in harmony to convert, combine, transport, and amplify light signals. While the fiber optic cable is the physical path, the following components provide the intelligence and muscle. 1. Optical transponder, wavelength converter. The transponder is the entry and exit point for data. It acts as an OEO, optical converter. Function: most client equipment, routers or switches, uses standard 1310 nanometers or 1550 nanometers lasers that aren't precise enough for DWDM. The transponder takes this client signal, converts it to an electrical bit stream, and retransmits it using a highly precise laser at a specific ITU grid wavelength. Key task: it ensures each signal has its own unique color before entering the shared fiber. 2 DWDM Multiplexer, MUX. The multiplexer is the on-ramp for the highway. Function: it is a passive device that takes multiple individual wavelengths from different transponders and combines them into a single composite optical signal. Technology: usually built using arrayed waveguide gratings, AWG, or thin film filters, TFF, to combine the light waves without interference. 3 DWDM Demultiplexer, DMUX. The demultiplexer is the off-ramp at the destination. Function: it receives the composite signal from the long-haul fiber and splits it back into individual wavelengths, sending each to its corresponding transponder or receiver. 4 optical amplifiers, EDFA/ROADM. Because light loses strength as it travels through glass, attenuation, amplifiers are placed at regular intervals, typically every 80 to 100 kilometers. EDFA, erbium doped fiber amplifier, the most common type. As discussed previously, it boosts all wavelengths in the C-band simultaneously without needing to convert them to electricity. Raman amplifier, often used in conjunction with EDFAs for very long distances, it uses the transmission fiber itself as the medium for amplification. 5 OADM/ROADM, optical add/drop multiplexer. These are placed at intermediate cities or nodes between the two main endpoints. Fixed OADM can drop a specific, predetermined wavelength to a local office and add a new signal on that same wavelength to continue the journey. ROADM, reconfigurable OADM, a modern, software-controlled version. It allows network engineers to remotely change which wavelengths are dropped or added without physically visiting the site. 6 Optical Supervisory Channel, OSC. This is the nervous system of the DWDM link. Function: it is an additional wavelength, usually at 1510 nanometers or 1625 nanometers, that sits outside the data carrying band. Purpose: it carries management data, such as equipment health, fiber break locations, and remote software updates, ensuring the engineers can monitor the line even if the main data channels are down. Component Summary Table. Component Short Name Analogy Role Transponder OTU/OEO Passport Control standardizes signals to specific colors. Multiplexer MUX Highway on-ramp merges multiple colors into one fiber. Amplifier EDFA Fuel Station boosts signal strength for long hauls. Add/drop MUX ROADM Exit ramp selectively picks signals for local use. Demultiplexer DMUX Highway off-ramp